underpinnings of the variational autoencoder and then see how we would actually implement them via DNNs. Again, the whole point is just set things up. You kind of have to go and look at the original papers and the follow-up papers and the code to actually get a working sense of how this is done. So the first thing is, of course, I'm going to take my data, and I have an encoder which I'm now going to model as probabilistic. So it's a probabilistic mapping given the input data point to a latent vector z, okay, or embedding z. And similarly, the decoder is a probabilistic map from the latent space to the data space, right? So we'll design the encoder, this guy. We'll design it, choose it from a tractable family, so something that I can parameterize. So I'll approximate it by qz given x. This p of z given x is some real thing that is out there, and qz of x is I have to choose a tractable member of this class, and this q sub theta, but I won't get into that notation. I need to choose a good qz of x to do my encoder. And the other thing I want is, because I want the decoder to work to generate artificial data, how will I actually generate it? Well, I need to draw random vectors here, and so I want p of z to be nice. For example, Gaussian 0i. So I definitely want that. And how about this decoder functionality, this guy? Well, I also want, in order to, model this in some nice way using a DNN, this also has to be chosen to be tractable, and that means that I might not get the best possible answers here. I might actually be limiting myself into what I can do. But we will make certain choices that you'll see in order to ensure tractability. So when we are trying to fit these models to data, of course, one way to do it is say, hey, whatever the parameters of the model are, so let me choose them to maximize the likelihood of the data I'm seeing. So the maximum likelihood approach is, of course, a very powerful approach. And we've seen, for example, that when it's intractable, sometimes we can approximate it, and the EM algorithm was one example of it. I'm going to now talk about another, actually not closely related approach to approximate it and see how that leads us to an optimization problem that we can actually solve. So to do that, let's start with what is the distance between my approximation for the encoder, that is a probabilistic encoder, q of z given x, and the actual guy. Right? I want to look at that. What is that? The information theoretic, the KL divergence between those is the expectation evaluated using the Q distribution of the log of Q of z given x divided by P of z given x. Presumably, if I choose this Q from a rich enough family, I can make this small. So what I want to understand is, how does this relate to the likelihood function? Basically the likelihood P of the probability of the data I'm seeing, or the log of the probability of the data I'm seeing. I don't know P of x. I don't know anything really right now. So I'm going to start by saying, suppose I could approximate this P of z given x in some way by Q of z given x, never mind how. How can I relate that somehow to this objective function that I have, that I want to maximize over whatever model I have for equivalent model that I'm inducing for this data distribution. Okay, so it's time to use Bayes' rule to deal with this term here. So P of z given x is P of x given z times P of z divided by P of X. So note that now my likelihood function is appearing in the denominator. That's good. I wanted it to appear somewhere. The other thing to note is P of Z. If I can somehow design my system so that my embedding is from some nice distribution that I know, that's also known. So we are getting somewhere here. So now I'm going to plug this in to the expression there. So I want to see what Q of Z given X divided by P of Z given X is. So that's Q of Z given X divided by P of X given Z times P of Z and multiplied by P of X, right? I'm just plugging things in from Bayes' rule. And let me write it down into terms that are grouped in a nice way. So I wanted the likelihood function, so let me write it separately. Then I have a Q of Z given X divided by P of Z term, which is both are densities in Z. And then I have a 1 over P of X given Z business here, okay? So I'm going to plug those in and note that I have the log there. So I'm going to, let me change pen colors. I'm going to plug all this into this expression, right? And I'm having trouble with this pen color, so let me... Once I plug it in and realize that I'm taking the log of this quantity, all these terms, these multiplicative terms decompose into addition, and what I get is this divergence term that I had. I'm going to rewrite it. Q and P Z given X is the expectation using the Q density of these, the log of these three terms, log of P of X plus log of Q of Z given X divided by PZ plus, well, there's 1 over that, right? So let me get rid of the plus. It's a minus log of P of X given Z. And note that if you give me the data, let me change pen color again. If you give me the data, this guy does not depend on the encoder approximation at all. So this just pulls out of the expression. And this is my log likelihood function that I'm really interested in. The second term here, this is the expectation using Q of the log of Q over this P. That's again a divergence, a KL distance. It's a KL distance between Q of Z given X and P of Z. And remember that P of Z is some desired density that I want my latent vector to come from. So that's actually known. And then I have minus the expected value under the encoder approximation of what's happening with the decoder. Right? So I have this guy happening. And now what I'm interested in is maximizing the likelihood function. So let me, write the likelihood function in terms of these other quantities. So I get that log of P of X is, I'm taking things over to the other side, expectation, let me emphasize that it's expectation using the Q density of the log of the P of X given Z term, right? That's just this guy taken over to the other side, minus the divergence between the Q density and the nominal density that I want my embeddings to come from, and plus the original divergence, right? Plus D of the approximation to the encoder and the actual conditional density that we are trying to approximate using the encoder. So that's nice. I get, I want to basically maximize the likelihood, so I have to maximize the right-hand side. And actually, this part I'm hoping, the last term I'm hoping I can make small, but I know that it's non-negative. So I can always say that the likelihood function is bigger than or equal to the the expectation under Q of this log term, and this I can we'll see that I can adapt using by adapting the encoder and decoder coefficients, minus how far is my encoder approximation, the stuff that is yielding at the output, how far is it from my nominal? That's this term. And indeed, this is what we will seek to maximize. This is a lower bound on the likelihood function, and for historical reasons it's called the variational lower bound, and it's come up in many different contexts that are broader than the current one. References that enable you to dig deeper are given there, but this is what we are going to try to optimize in the VAE. So how do we translate all this into a deep neural network, right? I mean, you have to parameterize things nicely. So basically, think about it. The encoder, your Q of Z given X, I want to take data points and produce embeddings from some distribution. Now, I don't really, know how to do backprop through an architecture like that. How do I do backprop from something that is generating random vectors? Z is a random vector given X. How do I do it? Well, what I do is to say, I'm going to assume that it's a random vector that comes from a nice density whose parameters depend on X. So what does that mean? I can take X and have a encoder deep neural networks that just produces M of X and C of X. Why? Because if you give me M of X and C of X, these are basically just a vector and a matrix, I can actually create a Gaussian random vector with mean M and covariance C by generating IID Gaussian random variables, right? So that's the first part of it. You basically assume a tractable thing. Once you have that, I can always say, oh, well, if you give me Gaussian 0 I random vectors, I can basically take these guys and say, okay, I'm going to add, I'm going to multiply it by C to the half, right? And add M of X to it and generate something like this. And they make a fairly big deal of it in the original paper. They call it the reparameterization trick, which allows you to do backpropagation through a deterministic network that produces a random vector. We also need to make some assumptions for convenience for the decoder. So remember that the decoder is supposed to take Z and have a probabilistic mapping to give you an X hat. I take a sample from this probabilistic mapping and give you X hat. I want to actually do it, of course, using a deterministic DNN that takes a Z and produces some function of Z. And basically what so DNN for decoder. So what I just will assume is that, hey, P of X given Z is actually just a Gaussian is just a Gaussian with mean f of z and white covariance. But this is a hyperparameter, right? So when you do that, your log of P of X given Z, remember that came up in our variational lower bound, that just becomes minus X minus its mean divided by 2 sigma squared, right? So plus some constants, additive constants that we can throw away. So all these choices, we have a relatively simple architecture that comes out. So basically, let me draw it out. It's there in the notes as well. So I have data coming into an encoder DNN that's generating both the mean and the covariance as a function of the input. I will then take the square root of the covariance matrix and multiply it by a randomly generated sample from Gaussian zero mean and white covariance, and then of course I'll add the mean to it, and that gives me a sample from Gaussian MC, right? Now I'm running out of room here, so I'm gonna break this up. The picture is very nicely drawn in the, or not nicely, but okay drawn in the handout as well. So I'm gonna take this sample and let me change pen color to. I'm gonna take this sample here, and let me bring it here, and feed it to the decoder. And what I'll get is x hat, which is a function of this sample. And now I'm going to change pen color again. I'm going to, how am I going to, what are the cost functions I'll drive? Well, one component of the cost function is how close is this x hat or f of z to the x in Euclidean norm. Remember, I had this this term. So this is part of the cost function that I want to minimize. That's one term. The other term is the divergence term in the variational lower bound, and that is going to measure how close is this embedding that's coming out of the encoder DNN to the desired distribution, which is Gaussian zero and white covariance. So this is the divergence between this MC and Gaussian 0I, right? So I have basically two terms in the cost function, and there's a weighting, remember there's a weighting 1 over 2 sigma squared here corresponding to the sort of nominal variance I'm taking in my parametric model. So I will have these two terms that will sum up in my cost function that I have to optimize. I realized that we had written down the variational lower bound a while back, so let me write it out again so you can see how these cost function terms in green are related to that. So remember that the log of the likelihood function was bigger than or equal to expected value under the Q distribution of the log of P of x given z minus the divergence of this Q distribution from the nominal distribution. And this is a maximization problem. Let me phrase it as a minimization problem, which is what I'm doing there. So what I'm really trying to minimize is a negative log likelihood, and instead I'm going to minimize this variational lower bound. So what I'm really trying to minimize is minus the expectation of Q of z given x log of P of x given z, and then plus this divergence term Q of z given x P of z, right? And this is where you can see that this divergence term is the term in green I had shown there. So I'm going to make a bit of a mess here and show this arrow. This is that divergence term between the I'm parametrizing Q by a Gaussian with mean mx and covariance cx. That's that. And then this term, if I'm saying that the output of the decoder is Gaussian with mean f of z and variance sigma squared per dimension. And look what happened. This expected value qz given x, meaning I go through the encoder, produce a z, and then I pass that z through this decoder, and then I get the negative of the log of the Gaussian density that I'm assuming at the output of the decoder, and that gives me this term, right? So now I have two fairly nice terms, and you can look at the notes for more details, but two terms such that now I can just apply back propagation and adapt both the encoder and decoder coefficients. As you can see, I mean, there is this attempt to be rigorous, saying, okay, I'm going to try to optimize something that is close to the log likelihood function, and that's sort of where we started. But then we made a bunch of assumptions. We said, oh, well, I am going to approximate the encoder output by a Gaussian with mean mx and covariance cx. In fact, we typically take this covariance cx to be a diagonal matrix, so it's characterized by just a bunch of variances along the diagonal. So that's even more restricted. And then I say, well, my decoder output is going to be again Gaussian, with the mean being a deterministic function of the embedding and the covariance being white, right? That's another restrictive assumption. So in principle, you could do better by changing some of these assumptions, and indeed VAEs have been improved by drastically changing the model for the encoder output, right? So people have actually the so-called VQ VAE schemes that have come out relatively recently, essentially do vector quantizations or sort of k-means on the output of a DNN for the encoder, and basically they optimize the cluster centers essentially using some kind of k-means. So we are not talking about Gaussian outputs anymore, and that turns out to do actually better in terms of say in domains such as images. You generate much sharper images doing that. So there's a lot of scope for innovation. One is not stuck to this particular parameterization, and this is a very active area of research. So I'm going to refer you to the handout for all further details, as well as references that you can use as a starting point for exploring further.